So thank you very much, Stefan, for your presentation. My name is Daniel Ramos. I'm an associate professor here in Spain in the Autonomous University of Madrid. And I've been using Bayes networks with the industrial application in the last years. I have been using Bayes networks in different contexts, also in different application fields. But this one is related, as Stefan was introducing, with power plants and in particular nuclear power plants. And this is a joint work between the Autonomous University of Madrid and ENUSA, which is a Spanish public company that deals with the issue, with the duty of providing of a nuclear fuel. Okay, nuclear fuel are these pellets of enriched uranium that is used in the nuclear power plants in order to make all these reactors that lead to the extreme heat that the plant needs to move the turbines to generate electricity. It is a very hot topic in Europe, electricity issues and energy and so on. And now nuclear power plants are again on the spot related to this energy, dealing with energy in Europe. So I hope this presentation will be useful for you in order to understand a little bit more how a nuclear power plant works and how we can use Bayes networks to improve the abilities of the operators and the managers of the plants in order to improve quality control in general. So let's start with saying that this presentation has been prepared from a journal article that you can see here. It's a journal on chemometrics and intelligent laboratory systems that we have presented jointly with the staff from ENUSA and our laboratory. So this is basically a presentation based on that. So if you want more details, you can go to the scientific journal and you can read it deeply in order to get more information or anything that I can present here. So let's talk about nuclear power plants, and in particular, a kind of nuclear reactors called pressurized water reactors. These kind of reactors have the duty of generating heat that is transported by water in order to make this turbine move. Okay, this turbine will move. That means that when this turbine is moving, there's a generator of electricity that produces electricity. So this is the part of the reactor where the nuclear fuel is. These are the bars of nuclear fuel that are reacted in order to generate extreme heat, a lot of heat, that is transported by a primary loop of water. This primary loop of water is not pure water. This is, in some sense, dirty or contaminated water. Okay? We'll talk a little bit about that. But this primary loop has the duty of generating steam for the secondary loop. So there are steam generators. This steam is transported, is brought to the turbine in order to generate movement and electricity. There is a condenser that brings back the water. This is clean water in the secondary loop. And this is the operation, very brief. Okay. There's a primary loop, which is, let's say, not clean, not pure water that is used to generate steam in the secondary loop. That is water. It's steam water that is used to generate movement in the turbine and then electricity. So this is how a PWR reactor works. So the issue is that this water is constantly in contact with the fuel, and the fuel is radioactive. And this radiation can have several effects in the primary loop itself, because there is some corrosion that is generated by some physical-chemical transformation. So, for example, the fuel itself can be corroded by the water because of the temperature and because of high radiation level. So also the pipes and the steam generator suffer from this corrosion. And this corrosion manifests into the water. It is deposited into the water in several ways, but one of the ways in which this corrosion is present in the water is by radioisotopes. So there are isotopes of some materials, mainly cobalt is a problematic one in this case. Cobalt that is deposited into the non-pure water, into the water that is recirculated again and again, is in some sense radioactive. And it's radioactive, and that has a lot of radiation in the reactor can be harmful for the staff that is in the duty of change the fuel bars or into the duty of open the reactor for maintenance. So there are some ways to alleviate this problem. There's, for example, this circuit. This is called the chemical and volume control system. That is a drain for this water, and it cleans partially the water. But because of some of the reasons of efficiency in the plant and so on, cannot be used intensely and has to be used in a controlled way. So this can in some way influence into the cleaning of this loop and into the reduction of the corrosion products of the radioisotopes. But it's not always the case, and it is difficult to predict in which to which amount this helps to reduce the radioisotopes. Because there is a discipline that tries to understand all this process, which is the chemistry of the primary loop. This discipline is aimed to control this primary loop chemistry in order to make the whole circuit safer and in order to make the whole circuit more efficient for the plant. But if there are, the main idea here and the message home for the rest of the presentation is that if there are radioisotopes here, this is an indicator of corrosion, which means that some of the infrastructure can be degraded and must be changed. And also it is an indicator of radiation dose for the people that is operating the power plant, which is definitely not desired and has to be controlled. And it's one of the main parameters of safety in the nuclear power plant, the control of the radiation dose when the operator comes to change the nuclear fuel, to charge the bars, or comes to open the reactor and go into the reactor for maintenance. So the primary water chemistry wants to control these radioisotopes, among other objectives. So the main objective is introducing additives, chemical additives to the primary loop. These additives are injected in the primary loop in a controlled way by the operator or by the operators of the nuclear power plant. So we'll call this variable control variables because they are known and they can be used to be injected into the circuit and control the chemistry of the primary. So in this sense, we can control the pH in the water, which has some influence primarily from the first, I have to say I'm not a chemist. I'm an engineer and I collaborate with chemists. So I will apologize in advance if there is some imprecision in the chemistry issues that I'm describing here, because it's a joint work and I'm not an expert on chemistry, but I will try to do my best. So the pH in the water can be controlled by the injection of some additives like bore or lithium. And it has an influence in many ways in this mix that is water premise of the reactor. Then we can inject hydrogen, and then we can inject zinc. That basically both of them are used to control the mix, control the water in the reactor, and try to reduce the amount of. But if we inject too much zinc, too much H2, or too much bore or lithium, it can be hard. So we cannot inject as much as we can. So there's an optimum that we have to maintain. And we have to do it in order to optimize operation, but also ensure material integrity and reduce the radiation fields. So it's not only reducing those, but also optimize the operation of the power plant and ensure the integrity of the materials in the first. So the problem we have here is that although there are models, chemical models that donate control variables and radioisotope variables in primary circuits, there are models that make some assumptions that cannot be assumed in a real scenario. Because in a real scenario, there are lots of interactions that are not easy to model or even known that can influence what is the outcome of introducing these additives into the water. So in some sense, there is lots of knowledge about that, of course, because safety in nuclear power plants is essential and it's paramount and everything is extremely controlled. But there's a need by NUSA to increase this knowledge about what are these interactions that may be happening into the primary loop, or in some way related to our research, how can we predict what would be the radioisotopes concentration when we manipulate the control variables? Okay, so we can do it in some ways. In two ways. We can fix the control variables and see what happens with the radioisotopes. or we can fix a desired value of the radioisotopes and have an estimate of what would be the value of the control variables that we have to set. So we can do both things. All right. So our solution, we are engineers, we are computer scientists. So we try to solve things using data-driven techniques in our laboratory. And we evaluated several solutions. And the best we achieved is to use a Bayesian networks because several reasons. Bayesian networks are interpretable. And this is important when there's people that is not proficient on computer science or machine learning models or artificial intelligence, like chemists, for example. They like to know what are the relationships among the variables in a explicit way, in a graphic way. And also because of the probabilistic nature of the network that allows the predictions with some kind of confidence bars, let's say. That can be very useful in order to, in some way, not giving too categorical predictions and try to, in some way, manage uncertainty of the prediction. So this uncertainty are managed because of the probabilistic nature of the network itself. So we will assume that the radioisotopes are latent variables. So we want to know their value, but we don't know yet. And the control variables are observed. These variables that we can control as operating the power plant in any or other way. Some of them are additives or consequences of using additives to the mix. Other are basically activations of these letdowns of this circuit, of this cleaning circuit of the loop, or even though the power generated by the reactor at that moment. So all these variables are in some way controllable and definitely observed. So these are the variables that we have observed. These are the variables that are latent. And at the first approach to this problem, we tried a Bayesian network that was fixed by the expert knowledge of the people at ENUSA. So that they suggested that the control variables would be connected to all the radioisotopes and the dependencies will be established in this way. So the structure of the network was fixed. At the end of this presentation, we will talk about the possibility of trying to infer the structure from data. Are working in progress to achieve that. But in this research, we fixed the structure and we train the parameters of this structure. So this is what we call a static network, which is pretty simple in some ways, pretty symmetric and pretty, it's not fully connected, but it has a lot of connections. But we tried also to introduce dynamic information to the network. So we will talk about the dynamic Bayesian network later. Okay. So we have our database, which is available from ENUSA. It's also property of ENUSA. It cannot be disclosed, of course, and it's confidential, but we can describe it. So it's a realistic database from 5 different nuclear power plants in Spain. In Spain, there are some power plants working currently. So from those power plants in Spain, this data has been collected. So for confidentiality issues, and we will not disclose the name of the power plants, but there are 5 of them and are numbered. Plants 1 and 2 present a slightly different behavior than plants 3, 4, and 5 because of the policies of managing the chemistry of the primary loop in these plants. And they have between 3 and 7 operation cycles. An operation cycle is one period in time in which the reactor works with the same configuration of fuel elements. After a cycle, we can replace some of the elements that are that have been exhausted and replace them with some of new elements, or we can change the elements from position. And this is what the nuclear physicists do. And that could use a cycle. After the cycle, the reactor has to be operated in order to change the elements of nuclear fuel and aid at generating power in a more efficient way. Also, this database includes temporal acquisition of many different variables. So these variables are acquired in time with a given frequency. That is, well, it's not a frequency because they are not acquired in regular intervals. In fact, the acquisition in time is quite diverse and it's non-regular. It's not a fixed period. So there were some work of data homogenization in order to make the database usable from the point of view of the temporal acquisition. But we can find a time series of power in the plant, which is measured in percentage of power, maximum power that the plant is able to give. The derivative of the net down, let's say the flux through the to the circuit used to clean the primary loop, an amount concentration of hydrogen injected, an amount the pH in the primary circuit water, an amount of the zinc injected in the mix, which is only present in plant 4 and 5, because this is plant 3, 4, and 5. These 3, 4, and 5 are the plants that this type of 3, 4, and 5 are the plants that inject zinc. Also, we have the radioisotopes: cobalt 58, cobalt 60, and chrome. The most important ones are cobalt 58 and cobalt 60, and in particular cobalt 60 because of the radiation, the times in which radiation becomes sufficiently low, which is a big amount. It's a big time in the cobalt 60. And these two are the main responsible of the radiation fields during operation of the reactor. And also, the radioisotopes are considered in soluble and insoluble form, and both forms are added. This is basically two forms in which these radioisotopes appear in the mix in the water of the primary circuit. And the temporal acquisition times had to be homogenized, and we interpolated also the control variables, because the control variables were measured at different times. These variables that are these 5 first variables were sampled at different times, and these had to be interpolated in order to make them more homogeneous. Okay. Also, you have the article if you want more detail on this, which is publicly available in this link. Moreover, we will exploit the temporal information, the time information, the dynamic information, or using a dynamic Bayesian network, which is also Gaussian, because all of the variables are continuous. Some of them can be easily categorized. For example, the power, most of the time is close to 100%. It could be categorized to make it a little bit more usable. But in some way, the variables have a continuous nature. So categorizing all the variables was not an option for us because of many reasons, but we didn't want to lose lots of information because the database was not incredibly big. And we didn't want to lose too much information by categorizing. So the point is that we tried to do something that could handle continuous distributions. But continuous distributions are difficult to handle in Bayesian networks. And in that sense, we have to do some transformation on the data before using a Gaussian Bayesian network. Gaussian Bayesian network is very, very easy to use in many ways because we have the linear Gaussian model. That is a very nice model to handle Gaussian Bayesian networks, and it works very nicely. But if all the variables have a distribution that is not Gaussian, then we have a problem by using the linear model. So we will see after some slides, we will see what we can do in order to Gaussianize. Also, we introduce a temporal dependence. So the dynamic Bayesian network can be connected by other twin dynamic Bayesian network, time TP, which is the time past the last time in which the data was acquired. This is TP, and this TP time can, in some sense, reflect this temporal dependence with the past values of the radioisotopes and the control variable. Okay? So this exploit time information in some way. That does not restrict the Bayesian network to a given moment in time, but to past times also. So, sorry. About Gaussianization, none of the distributions of the variables in the database were Gaussian, and the Gaussianization was done using a histogram-based technique. So we use what we call marginal Gaussianization. We Gaussianize the variable, assuming independence among them, which is not true, but Gaussianizing the variables independently does not destroy the relationship between the variables. So what we do is reflected here in this chart, initial signal. You can see the signal. I think it's one of the cobalt 58 signals, the plan. And then After that, we can in some sense model the empirical cumulative distribution function, which is on the right at the top. And then after we model this cumulative distribution function, what happens is that we can apply this function into the data itself, and it will become uniformly distributed. And after that, we apply another inverse transformation with Gaussian noise, with a Gaussian cumulative distribution function inverted, and we obtain a Gaussian histogram. So in some sense, if we have this transformation, which is based on the cumulative density function, which is empirical and also smooth, we can invert the transformation. So we can, in some sense, transform all the variables into a Gaussian domain where we can use a Gaussian Bayesian network to do the predictions. And after that, we move back to the chemical domain where the distributions are not Gaussian, which allow us to interpret the results again in the chemistry field. Okay. So in that sense, this is quite interesting. So the Gaussianization works in the following way. You have the initial signal, compute the cumulative distribution function. We apply this function to the histogram, which is basically, so we're inverting the distribution of this histogram. We obtain a uniform histogram. And if we apply an inverse Gaussian distribution, we obtain a Gaussianized system. Okay? This is how this works. After this, we will go into a Gaussian domain for all the variables, in which all the variables are suitable for a Gaussian Bayesian network. That is very easy to work with a linear Gaussian model. We perform the inference in the Gaussian domain, and we come back to the chemistry domain, applying the inverse transformation for all the variables. So that allows interpretability of the variables in the chemical domain, which is paramount for the people that will be operating this kind of algorithms that are basically chemists. This is a plot of the distribution of the variables before Gaussianization. So we can see here the pH, the differential of the letdown, power of the power band, H2, hydrogen, the radius of the cobalt, and the chrome. As we can see, the distribution is not Gaussian, or at least it presents lots of outliers and it's distributed. Even scattered plots are not very beautiful in the sense that are not resembling known distributions, so it cannot be easily modeled as Gaussian. After the Gaussianization transformation, we obtain this. That is not perfect. There are some of the variables, like the power, for example, that cannot be easily Gaussianized, but the rest of the variables are Gaussianized in a quite systematic way. And also, after the Gaussianization, the scatter plots are much more suitable to be Gaussianized in some. So this helps a lot to make the relationship of the variables to work in the Gaussian domains without losing the relationship between them. For example, you see here the relationship between the cobalt 60 and the chrome. That is still a very positive correlation here. You can see here a 0.85 correlation. Here you can see correlation also. So it is in some way going into the task of making the variables Gaussian without losing the dependencies between them. Of course, the control variables have some correlation between them in some of the cases they're not, but we'll try to make this whole thing suitable for the Gaussian Bayesian network to perform the prediction. Okay, so the experimental protocol basically is summarized here. We have the database. What we do is our database is not huge in number of data. That's one of the reasons to select a Bayesian neural network instead of something like a Bayesian network instead of a neural network or something like that to do this kind of estimation. And what we do is to perform some kind of cycle-wise cross-validation with the data. So we take one of the operation cycles for each plant is used as test data, and the rest of the data is used for training. And with the rest of the data, we train the Gaussianization transformation, and we train the parameters of the Bayesian network. And the results for all the cycles cross-validated in this way are pooled together for final results of prediction accuracy and prediction and log9 that we'll see later. This is a very realistic training protocol, and it is confirmed with the staff from ENUSA, because in some way we're predicting one cycle with data from other cycles, which is quite realistic. So where we have these past cycles of the nuclear power plant, and with these cycles, we need to have the prediction of the next cycles. And the database is small, and it's not small because there will be the possibility of having tons of data of the database. Each operation cycle takes years. So if we want to do this realistic protocol of cycle-wise cross-validation, we will have a very limited amount of cross-validation folds. And also, when you change, for example, the steam generators of a reactor, something that is done regularly in the operation of a nuclear power plant, then the radioisotopes in the mixture of the PWR of the primary secret water changes dramatically because the steam generators, they are corroded. And if you change them for some generators that are new, then you will have clean generators and the radioisotope will go down. So probably this new cycle will not be in some way fair for predicting future cycles with the same, with a different behavior. So basically the conclusion is the database will be linked indeed, and we cannot do too much for improving it. So we take the database, we do the cross-validation, we select training data and test data. With the training data, we clean up layers, we differentiate the letdown, do the interpolation of the control variables, Gaussianize. And with this Gaussianization, we train the model, the Bayesian network, and we train the Gaussianization transformation. We apply the Gaussianization transformation to test data, and we perform the inference on Gaussianized test data. And after that, we invert the Gaussianization and we evaluate the results. So let's go to the results. This is an example of predictions in time for the isotopes in the nuclear power plant. In one of the plants, this is plant 4, and this is one of the cycles of plant 4. The prediction has been done with this cross-validation procedure, which is fair in some way, in the way of separating training and test data. And we have the predicted isotopes in blue and the real value of them in red. And these bands are confidence bands of 2 standard deviations. And of course, we obtain values that are inside the confidence bars, which is good news. And also we obtain values pretty close to the values of the cobalts, which is also good news. So the predictions are quite good in general. So this is very good for ENUSA. We were very happy when they knew these results. And they use these prediction tools that we generate the software with these prediction tools for them. We transfer them to them, and they are currently using it in an evaluation stage. So here we can see also the variables and its evolution in time. This is the pH of the plant. This is the differential of the letdown. The power, which is most of the time 100%, but in some places it becomes lower because the plant is changing the operations and so on. And you have the H2, the zinc, and so on. Then you have the root mean square error of the prediction with respect to the real value. Okay, here you have, this is one measure of the prediction. The other measure will be the log likelihood in the Bayesian that we're going to see whether the fit of the model to this Gaussianized data is good enough. So these are values of a root mean square. And here we see the 5 plants for the cobalt 58 and the cobalt 60. And we can see how introducing different new variables from the initial state of one variable that was basically one network that was basically a very basic one, and then introducing dynamic information, which is the DBA part, is decreasing the error. In some ways, this error is decreased because of the use of Gaussianization. In some of the plants, it's because of the differential of the letdown, and in some of the plants, it's because of the dynamic nature of the network. But all of it together, it make the whole algorithm reach acceptable values of root mean square from the point of view of the operator, from the point of view of ENUSA and their clients that will be using this for prediction. Also, we see that incorporating further pastimes does not consistently improve root mean square error. So we tested to introduce more dynamism in the network. So not using only the past acquisition time, but the second past acquisition time and the third past acquisition time included into the network. So make the dynamic Bayesian network more and more complex. And we see that the root mean square does not particularly improve because of that. So we see an improvement by introducing the dynamic information, but introducing the dynamic information more than the past acquisition, that will improve, particularly in the performance, in the accuracy, the root mean square. Talking about log likelihood, we see that we introduced just the first past acquisition. The log likelihood can stay in lower values, negative log likelihood, which has an interpretation of error fitting. That in some way it has lower values that if we introduce more and more acquisition times, which makes sense because the more acquisition times makes the Bayesian network more complex with more parameters that have to be trained. And we have a limited amount of data. So probably we are in some way having sample size effects because of that. Finally, we decided to compare our Bayesian network with another algorithm that is very popular right now, which are the neural networks that are used in many applications in order to check whether our Bayesian networks is a good solution compared to just use a neural network, which would be in some way a very straightforward solution, and which in some way it's a very evident solution because of the popularity of the algorithm. So we compare our performance with a neural network with more or less the same amount of parameters. So it's a neural network with an input layer of 4 or 5 neurons, hidden layer of 4 neurons, output layer of 3 neurons. And if we compare our Bayes network with the neural network, we see that the root mean square error in general is comparable or worse in the neural network rather than in our network. In some way, very, very clear. So the performance of the Bayesian network is similar or even better of the neural network in some of the plants, but also the Bayesian network allows for interpretation and also allows for the flexible inference among variables. So a neural network, you have an input and you have an output. You cannot infer the input from the output in general. So with the Bayes network, you can flexible infer any variable with any other variable. So you can observe any variables you like and infer the latent variables from the observed variables in a flexible way, which is finally, conclusions. We have used a dynamic Gaussian Bayesian networks to solve an industrial problem. We have used marginal Gaussianization to being able to use a Gaussian Bayesian network with continuous data, which is a handy tool because it allows to use continuous Gaussian Bayesian networks with any variables with any distribution if they are well modeled as Gaussian after the Gaussianization process, which is not straightforward, but it is a handy tool if that happens. And as future work, we want to use structural learning to discover relationships between the variables in the network using a fixed structure for neural network by using structural learning to discover the relationships. And we want also to use those structures to predict radioisotopes also. Because in that sense, I think this could be research that will give a more useful and complete use of this dynamic Bayesian network, because discovering relationship between variables is also these fields where the interactions are not clear. So finally, I would like to thank all the people in this laboratory and all the people in Industrias Avanzadas that have contributed to this project. And this work has been supported by a collaboration with the two institutions. So thank you very much.